Massachusetts and Dartmouth, and the title of his talk is Young-Mills Gravity and Accelerated Cosmic Expansion.
The previous one, not as simple as you said. Okay, today I'm going to explain some new viewpoint related to gravity and accelerated cosmic expansion. First, I try to give you some review to explain the motivation. Thank you. After explaining the motivation, then I'll explain in what sense I'm talking about a generalized gauge symmetry. Then I'll present some new viewpoint to you. A basic picture of space-time. This is mainly related to the space-time with zero curvature, and the reason for this will be clear in a minute. There exists a fundamental flat space-time symmetry framework which can encompass all interactions in physics, including gravity, and is valid for both inertial and non-inertial frames. The second basic property is that we try to present a unified picture of all forces. That means there exists fundamental gauge symmetry which dictates all basic interactions in nature. By this I mean, for gravity, I'm going to follow Yang-Mills and Uchiyama's ideas to generalize it. And in this generalization, we use an external space-time translational gauge symmetry, that is a T4. You know that in the conventional gauge symmetry, according to the work of Yang-Mills and Uchiyama, they are the gauge symmetry for internal group. All the internal gauge symmetry associated with this gauge group. Mathematically, it is defined that all those group generators can be represented by constant metrics. Those are the traditional gauge symmetry within the framework of Yang-Mills and Uchiyama. Now, the first generation I'm talking about is to bring in external gauge symmetry. That is the space-time translational gauge symmetry, and show you that it worked to bring in gravity into the framework of quantum mechanics and the field theory. The second interactions I'm talking about is the well-known electron-weak interactions. This one has a potential symmetry breaking, and the third one is a strong interaction force, QCD, involving the SU3 color symmetry. The fourth one has not been discussed before because this is very strange. The gauge field associated with the baryon quantum number has been first discovered by TDD and C.N. Liang around 1955. And they follow through this formulation and find out that the new force presented by this baryonic gauge field is about 1 million times smaller than gravitational force. So in that case, there is no observational effect whatsoever. But in this case, I try to generalize this in order to say this new gauge field actually could enable us to understand the cosmic accelerated expansion. And I'll explain why. Because in this case, one also needs to bring in a generalization of gauge symmetry. The unified model here I'm talking about clearly is following the idea of Grashow, Salam, Ward, and Weinberg. In a sense, you just put different force associated with different gauge group together. And you say, this is not unification in the sense of Einstein and others. They all require that all the forces must be generated from the same constant, but that cannot be done. Especially in this case, when the group involving external group, like space-time translation group, and the internal group, like H2 cross U1, it is impossible to have a one D group which can encompass all these different subgroups. It's just impossible. So the most convenient or simplest way is just put them together, and you will see that when we put all these forces together, actually the finally exact symmetry is the only T4, space-time translational gauge symmetry is exact. All other symmetry will be violated very small by a gravitational effect. But all those small violations, we cannot detect them because their effects are so small. So summarize this, I will just simply say that symmetry appears to be the deepest foundation for our understanding of physical universe. In general, I would say that there are two basic frameworks in physics. One is a fresh space-time. That's all field theory for electroweak strong interaction all belong to this one. The second one is the curved space-time that, for example, Einstein's gravity is one of them. And in these two, I'll explain that Einstein's symmetry principle of general coordinate invariance, it is a profound idea, but it also has highly non-trivial difficulties. Why is that? For example, if you look at the explanation by Freeman Dyson, he's one of the founders of QED together with Tomonaga, Schwinger, and Feynman. In 1972, American Physical Society invited him to give a talk about the physical problem. And one of the problems he presented as a challenge to mathematicians is this one. He said that the most glaring incompatibility of concept in contemporary physics is that between Einstein's principle of general coordinate invariance and all the modern scheme of quantum mechanical description of nature. This is one problem he presented 30 years ago, and nobody was able to give a satisfactory answer so far. Okay. So this incompatibility is a motivation for our research. The second one is explained by Wigner, and I thought he gave us the best explanation about this second difficulty. He said that the basic premises of this theory, means general relativity, is that the coordinates are only auxiliary quantities which can be given arbitrary value for every event. Hence, the measurement of position that is of space coordinate is certainly not a significant measurement if the postulate of general theory are adopted. Most of us have struggled with the problem of how, under these premises, the general theory of relativity can make meaningful statement and prediction at all. This is a very non-trivial problem because people knew that long ago, and somehow we just associate with an experimental number to the coordinate even in general relativity. But he said that this is not to be allowed because if you adopt the principle of general coordinate invariance, you don't know what is significance of the number you attach to this coordinate of space-time in general relativity. The other one is related to another theorem, which there's a so-called theorem 2 in her 1918 paper. He showed that there's no conservation of energy in general relativity. And she also made a comment that this conclusion is consistent with Hilbert's observation, because Hilbert made an assertion without proving. He just said that he is the first one to write down the Hilbert-Einstein Lagrangian, and in this Lagrange, he just said that within this framework, you just cannot have the conservation of energy. But he just makes such a statement without proving it. So in a sense, neither prove it from the viewpoint of group theory. So if you look at this and say, why is gauge symmetry in flat space-time so successful for modeling all interaction except gravity? And to answer this is that it actually is simple, because when we are talking about the gauge symmetry, we are always talking about the internal gauge symmetry. So now, this Yang-Mills gravity I'm talking about is related to a generalized Yang-Mills symmetry. This is this formulation of this framework enable us to have a unified picture for all forces of gauge symmetry, because now we are able to bring in the gravitational force into this framework. So let me just mention this for symmetry. The Yang-Mills gravity is based on space-time translational gauge symmetry, T4, and electroweak force is Hu2 cross U1. Strong force is QCD Hu3 color symmetry, and there are baryonic forces and leptonic force. These are associated with U1 gauge group, and these are the forces which enable us to understand why, in a very large scale, these are accelerated expansion of the universe. These two, I will show that they may be responsible for that. Just to illustrate this idea, just to generalize, illustrate this generalized gauge symmetry, I'll talk about 1 and 4. Okay, gauge symmetry in flat space-time, a generalization of Yang-Mills internal gauge group to including external gauge symmetry, and this is a flat space-time. It is also a profound idea in the sense it actually can bring in all the property that we understand about gravity into the quantum mechanical framework. Now, what we say is this: look at this. In local space-time translation, it is x mu transformed to x mu plus lambda mu x. This lambda mu x now is a local function of space-time. Okay, and I'm using the Minkowski symmetry tensor because first let's consider this as in flat space-time, and I will also use natural unit. This lambda mu is an infinitesimal arbitrary function of space-time, and the four-dimensional displacement operator is p mu, and this p mu is I times dvx nu. Okay. Now this generalization brings two different things into the gauge field associated with T4. The first, the T4 gauge symmetry dictated the tensor field phi mu nu. It is not the vector field, because all the gauge field associated with internal gauge symmetry are the vector field or isovector field. Okay. The T4 gauge covariant derivative is defined in this. So it is ordinary partial derivative replaced by ordinary partial derivative minus Ig phi mu nu p nu. The reason we must have phi mu nu because p nu has a Lorentz indices there. So you cannot have this T4 gauge symmetry with vector field. You must have tensor field. And this tensor field is just the property we need for gravity. The second thing is, look at this. P nu is a momentum operator. It has a dimension. The generator for other internal gauge symmetry, they do not have dimension. But in this case, this has a dimension. So the coupling constant associated with this tensor field G also has dimension. And the dimension is just right. It's just right. You can think it this way. G will be related to square root of Newtonian coupling constant. Because when you look at this from the viewpoint of quantum field theory, the gravity is generalized by the exchange of virtual graviton between two vortices. And in Feynman diagram, each vortex contributes G. So the gravitational interaction effectively contains G squared. And this G squared in the first order approximation is equivalent to Newton's coupling constant Gn. And also this tensor gauge field is a symmetric tensor. Okay. Now, I'd like to emphasize this. If you look at this this form, you can look at this from two viewpoints. The first one, it is a local shift in flat space-time, because we just replace a constant shift in space-time replaced by a function of space-time. Okay. And also, this transformation is what you see in the tensor analysis. You can consider it is an arbitrary infinitesimal coordinate transformation in flat space-time. But this form is exactly the same form as what you see in general relativity. So in general relativity, this transformation is considered as an arbitrary infinitesimal transformation of coordinate in curved space-time. So we start from the same mathematical transformation, but view it differently, and it will lead to different physical results, as I'll explain later. So this one, it is a key conceptual departure from that of general relativity. Actually, the early discussion of gravity based on space-time has been discussed by many people, by Rogunov in Russia, and his student in Moscow State University, and from Yeoman Chen in Korea, and Wu Ning in Academy of Science, Beijing. They all discussed this before, but it seems that their discussions are closer to Einstein's approach, because eventually when they try to write down the equation they derive from a Lagrangian, that Lagrangian is more closely related to the Einstein Lagrangian, Hilbert Einstein Lagrangian. But from my viewpoint, based on these two are completely different ones, because it is now in the framework of flat space-time. And this interpretation actually can be done in both inertial and non-inertial frames. But for simplicity, that means just concentrate on the inertial frame. Okay. So the T4 gauge symmetry postulates the replacement of the Lagrangian with ordinary derivative replaced by this gauge covariant derivative. And this gauge covariant derivative can be written in this form. It is J mu nu times ordinary partial derivative nu. And this J mu nu is a function of Minkowski metric tensor and the tensor gauge field dictated by the translation gauge symmetry. And as I said, this G up here is not dimensionless, it is a dimension of length, and phi is not a vector field. So these properties, they differ from the usual Yang-Mills gauge symmetry. Okay. One comment. If you know quantum field theory, you know that if a coupling constant has a dimension, then by the naive power counting, you know that in the higher orders, it almost always leads to non-renormalizable field. In this case, originally, I hope that since it is the T4 Yang-Mills type of gauge symmetry, I hope this symmetry will somehow make the high order divergence when I calculate Feynman diagram become more mild or even renormalizable. But so far from my experience, it is still not renormalizable because the coupling constant has a dimension. Okay, so the gauge curvature, I don't know whether I can. Oh, here. I just want to let you know that the gauge curvature C mu nu alpha, they are determined by the commutator of the T4 gauge covariant derivative. This is as usual when you try to calculate the curvature. The curvature, in this case, we are not talking about the space-time curvature, but it is the T4 gauge curvature, and it has three indices. and it is given by this. And they are, when you use them to construct a quadratic form of the Lagrangian, turns out there are two independent terms, and these two independent terms is the one just right to describe the perihelion shift and bending of light and other so on. So this is the first one. The two terms come from the symmetric tensor field, and this is the Dirac field. Okay. So the T4 gauge invariant field equation is given by this. This H mu can be expressed in terms of the gauge curvature in this form, and the source is in terms of the gravitational field in this way. My notation is not quite right, show up here. This will be the psi bar. Okay. So based on this, now let me just omit all the mathematics, just tell you what is the physical result of this. The first thing is that we are starting from a quantum field theory in flat space-time. So all the physics must be determined by this Lagrangian. You cannot make any additional assumption. So we say, what happened to the equation of motion for macroscopic body like a sun or the earth? It is quite interesting that when we are talking about the wave equation for the massive fermion or massive boson, we have the wave equation, but you take the geometric optics limit of this wave equation, they turns out give us this type of equation. It is the Hamilton-Jacobi equation with an effective metric tensor here. So that is quite interesting because we are starting from the flat space-time, but somehow the T4 gauge symmetry has the property that when you take the geometric optics limit of the wave equation gives us this equation. Then this equation tells us that the macroscopic object move as if they are in some kind of effective curved space-time with the matrix, effective matrix G mu nu. And this G mu nu is not the space-time curvature, it's not related to space-time curvature. Actually, it is related to the symmetric tensor field dictated by the T4 gauge symmetry. Okay. So this G mu nu appears only as only in the critical limit. Okay. In the non-critical limit, they are the quantum field in flat space-time. And similarly, when we consider the Maxwell equation, in the Maxwell equation, you take in the presence of gravity, okay, you take the critical limit of the Maxwell equation, and this means the geometric optics limit. Okay. We'll get Eichhorn equation, and this Eichhorn equation associated with a slightly different G mu nu. This G mu nu is not exactly the same as this. This is for mass not equal 0, but for the Maxwell equation photon, it is massless. Then this GL is slightly different. And this provides an opportunity for experimentally to test whether this idea of Yang-Mills gravity is correct or not. So from this, one can say that the effective curved space-time for the motion of critical objects in Yang-Mills gravity is the result of taking the geometric optics limit. Okay, as I told you that Hamilton-Jacobi equation for the perihelion shift, it is the same as the usual result within the experimental accuracy. Redshift is the same, and gravitational quadrupole radiation to the second order still the same. The bending of light are different. The bending of light, according to this Yang-Mills gravity, it is 1.53 seconds. The usual one is 1.75. So this result is about 12 times smaller than the usual rate, 1.75 seconds. And the experimental accuracy is about 10% to 20% for the optical frequency because of the difficulty in pinpoint the position of star with this atmosphere, the disturbance of atmosphere is not easy. But I hope that in the future, if the accuracy can put down, can be as small as a few %, then there's a chance to test this idea.
Sorry, what is the source of the difference for the light bending?
Hmm?
What is the source of difference?
Briefly speaking, the source of difference is that when you do the approximation, we impose for example, the Lorentz gauge condition, and this Lorentz gauge condition you impose when you take the geometric optics limit is leads to a slightly different effective Riemann curvature.
You don't have additional parameters. Do you have additional parameters?
There's no parameter.
But then,
The Lagrangian, there are two terms. The parameter is fixed there. So when we solve it to the first order is assumed to be identical to the Newtonian result. That fixes the parameter, the small g. Once the coupling is fixed, then there's no more parameter in the theory. The conclusion I'd like to say is that the total unified model is related to this one with this gauge group. And if we write down the gauge covariance derivative, the first two terms is related to the T4. All these other terms are the same as the usual H3 colors and Weinberg-Salam theory. That's the same as usual. So one new conceptual result of the Yang-Mills gravity is that the apparent curvature of space-time appears to be simply a manifestation of the flat space-time translational gauge symmetry for the motion of quantum particles in the gradual limit. That seems to suggest that this is a new viewpoint. I'll use 2 more minutes to explain this ideal expansion. The generalization in the case of the baryon conservation of baryon number, it is replaced by the usual scalar gauge function by a vector gauge function. So once you replace this, then the transformation for the charge field, this transformation involving not the ordinal phase, but it involving a path-dependent phase. This path-dependent phase has this form exponential minus IF and integration of this gauge function along a certain curve in space-time. The integration is such that you can take arbitrary paths as long as the endpoint of the path is the x itself. Then this defines the generalized gauge curvature. When you do it, then the most important one is now we have a path-dependent phase vector. And in the special case, when this vector function can be written as the space-time derivative of a arbitrary scalar function, then all these return back to the usual gauge symmetry. So in a sense, it is a generalization. So this is the gauge covariance derivative, and if you do the compute the commutator of the gauge covariance derivative, you get this B mu nu. The structure of B mu nu is the same as what we have in the U1 gauge symmetry. But now, you say, what is this quantity? This quantity turns out to be not gauge invariant. Why? Because when you make a gauge transformation, you have this B prime mu nu goes to B mu nu, but there are terms here. They are not zero in general. So what happened here is that we impose a constraint for the 4 arbitrary vector functions. The usual one is 1 arbitrary scalar function. Now we introduce 4 vector functions, so we make a constraint, and once you impose this constraint, then you will see that the divergence of the U1 gauge curvature is invariant.